To organize the process of requirements collection, feature specification, and tracking of changes, Semantic Web Company uses the Atlassian tools Confluence and Jira. The goal in the aligned governance use case is to express the information managed by these tools as RDF data using the aligned meta model. This will enable us to query requirements and issues in a standardized way by using Sparkle and to easily combine them with other datasets. For example, the process-related data can be annotated with concepts that's original from the taxonomy created in the Pool Party Thesaurus Manager. These annotations can help in increasing the quality of results when searching requirements documents or identifying similar requirements or issues. Semantic Web Company collects the requirements for each version of the Pool Party Thesaurus Manager in the Pool Party development space in a hierarchical form as shown here. The root page of the requirements documents is titled Requirements PP, which is on the next level, followed by pages containing high-level description of a specific feature, which again are followed by more detailed descriptions. Most of these pages are structured based on standard templates defined by Semantic Web Company. An exemplary high-level requirements description looks like this. It contains the title, a textual description of the goal from a user perspective, a list of steps that need to be performed to fulfill the requirement, and the involved stakeholders. On the more detailed level, the requirements pages are structured in a similar way. They contain a title, linked issues from the Jira issue tracking application, as well as a textual description from the user perspective. The specification also includes a list of preconditions that must be met in a more detailed description of the feature, containing text and mockups. Furthermore, a detailed requirements page also lists acceptance criteria and test scenarios and is usually followed by some comments discussing things that are not clear to the developers. When a requirement is specified so that implementation can be started, new documents, so-called issues or tickets, are created within the Jira application. This is an example of such an issue. It contains structured information about, for example, the type of the issue, its priority, the current status, and the responsible developer. Issues also contain a detailed description about what functionality they cover and optional attachments to better illustrate the problem or to provide test data. To represent the data contained in the Confluence and Jira installations as RDF, DIO, the Design Intent Ontology, is used by the Unified Governance tool implemented by Semantic Web Company. DIO has been created by Oxford Software Engineering as a part of the aligned meta model to capture the knowledge generating during various phases of the software design lifecycle. Oxford Software Engineering and Semantic Web Company have also created DIO-PP, which maps the pool party conceptualization with the DIO ontology. This is how the various parts of the requirements pages get converted into their RDF representation. The green frames around the page elements illustrate what information is represented by what elements of the vocabularies. While some elements, like the requirements title and goal description, can be represented by standard vocabularies such as DC terms, others, like the Jira issues to which a requirement is linked to, are formalized by attributes coming from DIO. Also, for detailed requirements pages, we can cover most of the information contained with DIO. Finally, we can also cover the content of Jira issues. For almost every element of the issue, we provide a way to map it to the standard RDF representation, making use of DIO-PP. To perform the actual data extraction and conversion process, we contribute 3 tools. A Java project that can be compiled as an application, which may be run from the command line, connects to the Confluence and Jira instances, and dumps the contained data in RDF format. The tool can also be compiled as a library to be used in other projects. This is required for our second contribution, a plugin for Unified Views, which wraps the data extraction library so that it can be included into custom data processing pipelines. Unified Views is an existing open-source extract, transform, load framework with a graphical user interface that allows users to define, schedule, execute, and debug RDF data processing tasks. As our third contribution, we provide such a unified views task which encompasses data extraction, data annotation using a pool party thesaurus, and loading the annotated data into a remote triple store. The extraction task is organized as a 7-step pipeline. In the first step, our extraction tool, indicated with the red box, is used to provide the data which should be annotated. The next processing step is the box below, which filters the extracted data so that it only contains text literals which serve as an input for the annotation API. It passes its output to the next pipeline stage, which is a processing unit that connects to the pool party extractor annotation API and returns a RDF graph containing the identified annotations for each resource. After that, the original extracted data and the filtered annotated data are merged and converted to a file. This file is then both written to the local file system for debugging purposes and uploaded to a named graph in a remote Virtuoso server so that it can be queried using Sparkle. Semantic Web Company provides a Virtuoso installation that will hold the extracted data in a named graph at aligned-virtuoso.poolparty.biz. Using Virtuoso's graphical user interface, the data we extracted can be directly queried by Sparkle. This allows us to run various statistical analyses. For example, we are able to find out the 10 issues that have stayed unresolved for the most number of days. In the future, we plan to use the annotations from the taxonomy to detect duplicates or similar requirements or issues. Our immediate next steps will cover the exploitation of the extracted data to formulate additional valuable competency questions. These will also drive the further development of the extraction tool as well as DIO and DOPP, because we expect the currently extracted data will not provide enough information for answering all of these questions. We especially want to identify misstructured or erroneous requirements so that we can increase the overall quality of the software development process at Semantic Web Company. In cooperation with University of Leipzig and Oxford Software Engineering, we will propose a methodology for linking the extracted Confluence and Jira data with the test cases, formalized as, for example, RDF unit tests, shackle shapes, or spin rules, which establish the link between the software development and the data development lifecycles.